Have you ever seen the chemotherapy process for cancer treatment? Or you ever notice smoke detectors in shopping malls? Do you know that they are relying on one powerful idea in physics, which is half-life? Now, half-life is not just a theory from your textbooks. It helps the doctors to safely use the radioactive substances in medical scan as well as cancer therapy. And yes, even something as simple as a smoke detector in your home uses a tiny bit of radioactive material that decays over time. Learning about half-life teaches you how the radiation behaves over time. So in your IGCSE Physics exam, you are always asked to interpret decay graphs, subtract the background radiation, as well as to calculate half-lives from the data. So in this video, I am going to focus on how to calculate half-life with and without the background radiation, and the simplest method, some tips that I'll share with you to determine your half-life as accurately as possible. Are you ready? So this video, I'm going to focus on understanding half-life, unlocking the secrets of radioactive decay. Right? But before that, let me tell you something. What if I tell you that banana was radioactive? Who likes bananas here? Everybody loves banana. Excluding me. I don't like banana, right? So I'm eating banana, but I don't like it, right? Do you know that bananas contain potassium 40, a radioactive isotope? Do you know that? But, okay, if you are a banana lover, don't worry, just be happy. Why? Because banana is safe for you to consume, right? It won't hurt you. But what if it decay fast enough for you to notice when you eat it or when you consume it? Right. So let us explore how the scientists predict and measure this invisible process. How about that? Right? Let us start with the definition of half-life, right? I used to play a lot of games. I know that half-life is one of the names of the games that I played, but half-life in physics has nothing to do with the game. Half-life is being defined as the time taken for a radioactive nuclide or radioactive isotope to decay to half of its original value or original activities or original count rate, right? The ones that are highlighted are very important keywords. Now, half-life, it has constant, right? It is constant. Half-life is constant for a given isotope. And the units of half-life could be in second, could be in minute, could be in hours, could be in days, could be in months, could be in years, depending on that radioactive isotope. Right, this is the decay graph. Half-life in action, right? Let us look at the graph. When you look at this graph, the decaying graph is always exponential. The graph of decay is always exponential. So just bear this in mind, okay? When you look at the graph, you have to understand right away when the number of half-life is equal to 0, this 100, the y-axis, shows you the initial count rate or initial number of that radioactive isotope. Now, how to calculate the half-life, right? So there are two ways, okay? One is without the background radiation. How do you calculate the half-life without the background radiation? And how to calculate the half-life with the background radiation, which is more complicated. But don't worry, I will discuss this one by one. Right, so let us look at how are we going to calculate the half-life without the background radiation. If the question asks you to calculate the half-life without the background radiation, things would be easier for you, right? So I'm giving you step by step on how to calculate the half-life without the background radiation. First step, you determine the count rate of the radioactive isotope first. Initial count rate is when the time is at 0. At 0 minute, 0 hour, or 0 second. So look at the time at 0 minute, 0 second, 0 hour, 0 days, right? And step two, after one half-life, you have to remember, since the decaying graph occur exponentially, right, the initial count rate or initial activity of the radioactive isotope must be half. Right, maybe a little bit confusing. I get you. Don't worry. I'm going to use some past year questions here to discuss. Right. Now, you look at this, one of these past year question right here. A reading is taken every 10 minutes of the number of emissions per second from a radioactive source. The table shows the reading. What is the half-life of the source? First thing you do is to read every word here. Is there any background radiation being mentioned? No. Then you know that, oh, no background radiation. Things is easier. Yeah, the thing is to calculate this will be easier. First step you do is you look at the time. Time at 0 minute. This is what we call initial number. Right, initial number of the radioactive source. Right, so write down, I'm going to write this down for you. Initial number is equal to 800, right? Numbers, 800 numbers of emission per second, right? So, okay. I just don't write that unit for it. Right, at half-life or after half-life, right? Okay, you write at half-life. This initial number has to decrease by half, right? So you just take 800 divided by 2, which is 400 emissions per second. So 400 emissions per second. Now, since the table is being given and no background radiation, yeah, mentioned here, just look at number of emission per second. Where is 400? This is 400. And what is the half-life? Half-life, it is the time. So it is 20 minutes. So 20 minutes is the half-life. Okay, maybe you want more question? Definitely, I am okay to give you more question. This is also one of the past year questions. A sample of radioactive isotope has an initial rate of emission of 128 counts per minute and a half-life of 4 days. How long would it take for the rate of emission to fall to 32 counts per minute? First of all, I am going to highlight this initial rate of emission, which is 128 counts per minute. Write that down. The way of me solving this question is that I didn't use any equations. I didn't use any formula, right? I just draw a table. My table is as simple as this. I just split up. Right, this is the, draw longer. So the initial rate, okay, I just put it here, 128 per minute. That occur at time equal to 0. And you know that since the graph is decaying graph, so 128 will have to reduce by half divided by 2. So you take out your calculator, take 128, divide 2, you get 64. 64, since you have divided by 2 once, this is one half-life, which is equal to 4 days. By the way, T1 over 2 represents the symbol of half-life. And keep on dividing until you get 32 counts per minute. So I would divide again, 2. This is 32. Since I have divided 2 twice, this will be 2 half-life. So 2 half-life, you take 2 times 4, which is 8 days. Can't you see? 32 counts per minute occur in 8 days. So C is the answer. What about this? What if the graph is being given, right? I talk about the table, I talk about the sentence, and what about the graph? The graph shows the count rate from a radioactive source over a period of time. What is the half-life of the source? When a graph is being given and no background radiation is being mentioned, right? First of all, look at time equal to 0. Look at the value on the y-axis, the starting of the exponent graph. It is 2000, sorry, 2000. 2000 is actually the initial count rate of this radioactive source. So just write it down. Initial count rate is equal to 2000 counts per second. And what is the half-life? If the question asks you about the half-life, at half-life, remember, half-life meaning to say that the initial count rate must reduce to half, right? So you take 2000 counts per second divided by 2. So that gives you 1000 counts per second. And look back at your graph. Where is the 1000? This is 1000. So 1000, look at the time axis. Okay, so it occur at 1 hour. So the answer is 1 hour. As easy as that. Now, what about things are getting more complicated? How to calculate half-life with background radiation? It is not to say very complicated. It's just that something you have to bear in mind. Just be careful when the background radiation is being given. Now, let me explain a little bit about the background radiation. Do you know that, okay, background radiation means that we are actually surrounded by radioactive materials all the time. And there are radiation around us all the time. The food that we consume, remember from the earlier slide, I talked about the banana. Banana contains radiation, right? And then the drinks that we consume, the building that we live in, right? The walls emit background radiation, emits radiation all the time. Background radiation is the radiation detected by detector. You just place a detector and detector will give you an initial reading before you bring in the radioactive isotope. That is background radiation. It is unwanted stray radiation. You don't know where it is coming from. Right. In order to calculate the half-life of the radioactive isotope, background radiation must be subtracted if the value of it is significant. Now we are going to look at how to calculate the half-life with background radiation. First step, you find the initial count rate of the radioactive isotope. How do you find that? Right. First of all, let me tell you first, detector, the detector that we are using nowadays, they are not selective. Detector, when you switch on, detector is not to select the radioactive isotope, to detect the radiation from the radioactive isotope. Detector will detect any radiation surrounding it. So that is why it is your job to find the initial count rate related to radioactive isotope only. How to calculate that? You take the initial count rate, okay? Detector readings, detector's initial detector reading minus the background radiation to get the initial count rate of the radioactive isotope. And after that, you know that after one half-life, the initial count rate of the radioactive isotope must be half, right? Let me guide you by using the past year questions. How about that? So let us look at this question. In a laboratory, a detector of ionizing radiation records an average background count rate of 8 counts per second. And then after that, a radioactive source is placed close to the detector. Count rate on the detector rises to 200 counts per second. What is the count rate due to the radiation from the radioactive source? So if you want to find the radiation due to read the question carefully. That is very important. Radiation due to radioactive source. Okay? Radiation of radioactive source is equal to detectors reading minus background count rate. So what was the detector reading? It is 200 counts. So this detector actually detecting the radiation from the radioactive source plus the background radiation. So detector reading is 200 counts per second minus background radiation is 8 counts per second. So you get 192 counts per second. B is the answer. The next one, right? Text no graph. It's just the long sentences, right? A radioactive source produces a count rate on a detector of 1,600 counts per second. After 32 hours, the count rate has fallen to 100 counts per second. Both count rates have been corrected for background radiation. This is a very good news. Count rate corrected for background radiation, meaning to say that you can ignore the background radiation. Okay, you do not have to subtract any background radiation because the count rates have been corrected. That means the background radiation have been subtracted. Right? What is the half-life of the source? First thing, right? When I see long sentences, I have to draw a table. So I'm going to draw a table. So started with 1,600 counts per second, right? At time equal to 0. That is initial count rate. Initial count rate occurs at time equal to 0. And then after one half life, right, divided by 2, right? The initial count rate must be half. Remember, that gives you 800 counts per second. This occur at one half life. I just put one half life because half life is not being given. And then after that, half again. That is 400 counts per second. Since I divided 2 twice, this is 2 half-life. And after that, half again. 400 divided by 2, that is 200. Since I divided 2 3 times, this is 3 half-life. And keep on doing until you get the count rate of 100 counts per second. So keep on doing. Okay, 200 divide by 2, I get 100. That occurs at 4 half-life. And 4 half-life, the time given is 32 hours. So you just use the math. 4 half-life is equal to 32 hours. 1 half-life, T1 over 2 is the symbol of half-life. 32 hours divided by 4, you would get 8 hours. The answer is C. Okay, attention, right? This is the one that I want to share with you. To use the graph, sometimes things are getting more complicated. In order for you to use the graph to determine the half-life, right? Because the graph shown are the readings from the detector. So I told you before that the detectors are not selective, right? They will measure the background radiation together with the radiation from the radioactive isotope. So in order for you to use back the graph, you have to add back the background radiation after the count rate is half. Okay, maybe sounds confusing, but don't worry, I'm giving you some past questions. Right here, let us look at the table. A laboratory worker measures the count rate from the radioactive source. He records his results in a table. Just if it is a table. Average background radiation. If it is given, you have to eliminate this. Background radiation is given as 8 counts per second. What is the half-life of the source? Okay, this worker. Okay, so the initial count rate, but I have to find the initial count rate due to the source because the question asked me for half-life of the source. At time equal to 0 minute, this is the initial count rate of the detector. Initial count rate of the detector is the count rate of the initial count rate of the initial count rate of the detector is the initial count rate of the radioactive source plus background radiation. So I need to find my initial count rate, okay, for radioactive source, only radioactive source. So which is equal to 100, the detector reading, minus the background, which is 8 counts per second. So when you minus it, you get 92 counts per second. This is the initial count rate related to radioactive source only, right? So at half-life, 92 counts per second. Initial count rate must be half divided by 2. So when you divide 2, you get 46 counts per second, right? Remember what I told you? In order for you to use a graph or use back the table, because the table given here is including the background radiation. Right, so to use table to determine half-life, background radiation is added. So you take 46 counts per second plus the background radiation, which is 8 counts per second. So you will end up getting 54 counts per second. 54 counts per second, the time taken is 2 minutes. So the half-life of the source is 2 minutes. That is how we do it. Okay, confused? Never mind. I'll give you another question. The graph shows how the count rate registered by a counter near to a sample of radioactive isotope changes over a period of a few days. Background count rate is 5 counts per minute. Right, what is the half-life of the isotope? Look at the graph. Look at the graph. I want you to see this carefully registered by a counter, a detector. So the graph included with the background radiation. Right, so every single values on the graph is together with the background count rate. So first thing you do, always look at, when a graph is being given, always look at the time first, 0 days. Take the initial count rate of the detector. Okay, this is the initial count rate of the detector, which is 45. So if you want to find the initial count rate of the isotope, okay, initial count rate of isotope must be equal to initial count rate of the counter minus the background, which is 40 counts per minute. And after that, step by step, at half-life, what happened? The count rate of the isotope, which is 40 counts per minute, must be half. So you divide 2, so you get 20 counts per minute. Remember what I told you? The graph is included. Each and every value on the graph included with the background count rate. So in order for you to use the graph to determine the half-life of the isotope, background radiation must be added back. Right. Okay. Half-life of isotope. Okay. From graph. Okay, you take the half-life of the isotope, which is 20 counts per minute, add back with the background radiation, which is 5 counts per minute. That is 25 counts per minute. Look at your graph, which is 25. This is 25. Look at the value of the time. That will be the half-life. 2 days is the half-life. A is the half-life. Most of the students answered this question wrongly, so you have to be extra careful when the half-life is being given. Right. Now, what about the next one? Okay, I give you more, right? I know that some of you might be confused, so I give you more. A student determines the half-life of the radioactive isotope. The student uses a detector over 5 minutes and plots a graph showing how the count rate shown on the detector varies with time. The count rate due to the background radiation is 30 counts per minute. What is the half-life of the isotope? Now, first step, still remember? First step, look at the time axis. Time is equal to 0. Take your initial reading on the y-axis. So this is 210, 20, 30. This is 230. 230 counts per minute. That is the count rate, initial count rate of the detector. So since the background radiation is significant, so you want to find the initial. You have to find the initial count rate of the radioactive isotope of radioactive isotope. How do you do it? Take the initial count rate from the detector, which is 230 counts per minute, minus the background radiation, which is 30 counts per minute. You get 200 counts per minute. 200 counts per minute represents the initial count rate of the radioactive isotope. Now, after that, what you do is that at half-life, the initial count rate must be half divided by 2. You get 100 counts per minute. To use back the graph to determine the half-life of the isotope, to use graph to determine half-life of isotope, radioactive isotope, you have to add back the background radiation, 100 plus 30. That gives you 130 counts per minute. Where is my 130? This is 110, 20, and 30, 130. And get the value from the graph. This is 1. Okay, this is 1.1, and 1.2. 1.2 minutes is the answer. Now, okay, bonus tricky question. This is one of the super duper tricky question. Even some of the good students, right, they will make careless mistake. Right, I want you to try this. Now, feel free to pause the video, right, in order for you to try it out first before you check your answer with my answer. Right, a radioactive material has a half-life of 20 days. A sample of material contains 8 times 10 to the power of 10 atoms. How many atomic nuclei have decay after 60 days? Now, again, I have to do my table. Right, so initial, okay, number is 8 times 10 to the power 10 atom that occur at time equal to 0. Right, and then at half-life, okay, it has half-life of 20 days and I want 60 days. So decreases half divided by 2. That gives you 4. 4 times 10 to the power of 10 atoms that occur in 20 days. One half-life, 20 days. And keep on dividing until you get 60 days. Divided by 2. This gives you 2 times 10 to the power 10. Can you see? It keeps on decreasing. The number of the material or the number of the atoms keep on decreasing. That is 2 half-life. 2 times 20 days, I get 40 days. And after that, divide, keep on dividing, divided by 2. That will give me 1 times 10 to the power 10. This is 3 half-life. Why? Because I have divided 2 3 times. So 3 times 20, I get 60 days. Most of the students, when they see this, oh, okay, 60 days, that is 1 times 10 to the power of 10. So the answer is A, right? So in a way, this is incorrect. Do you know why? Because 1 times 10 to the power of 10 is the remaining nuclei. The question asks you how many have decay? Right, the one have decay. This is remaining. Okay, the one that have decay, you have to take your initial value minus, right? Initial atoms, 8 times 10 to the power 10 atoms, minus the remaining 1 times 10 to the power 10, which gives you 7 times 10 to the power 10. So 7 times 10 to the power of 10 atoms have decay. Right? So that is all about the calculation of half-life and a little bit about half-life. So if you still feel that it is quite confusing and you need more positive questions, topical positive question related to half-life, feel free to comment below. And last but not least, next time when you hear the word radioactive, don't just think of danger, think of discovery in science that lets us understand time itself, right? That's the power of learning half-life, right? I hope you gain benefits from this video and thank you very much for watching. See you in the next video. Bye.